My name is Jose and I did problem number 36 on the related rates problems, and it's called filling two pools. So we have two cylindrical swimming pools that are being filled simultaneously at the same rate. The small pool has a radius of 5 meters and the water level rises at a rate of 0.5 meters per minute. The larger pool has a radius of 8 meters. So how fast is the water level rising in the larger pool? Okay, and here's a little diagram of the problem. So as we can see, the bigger pool has a radius of 8 meters, and then the small pool has a radius of 5 meters. And then they tell us that the change in rates are equal. So we can start doing this problem by knowing what they're giving to us. So we know that they're giving to us the radius of the big pool, which is 8 meters, and the radius of the small pool, which is 5 meters. They also give us the changing rate of the rising water of the small pool, which is 0.5 meters per minute. What we need to find is this is what we need to find: the change in rate of the rising water of the big pool. So this is what we're gonna try to find. We're trying to find how fast is the pool rising, the water level is rising in the big pool. So here we can start by labeling things to help us figure the problem out. So we're gonna figure the problem out by using the volume of the equation. And here's the formula for the volume of the equation. It's volume equals pi r squared times h. So we know that. So I labeled ds dt for the rate and change of the small pool, which is 0.5 meters per minute, and then we're trying to find the rate and change of the big pool. This is our main goal. So how are we gonna do that? So we're gonna start by putting both of the equations equal to each other, since they told us that the inflow rate are equal. So I can say both of the volumes equal to each other and solve for dv dt. So here's my two equations of the volume. Is dv dt equals pi r squared db dt for the big pool, and then db dt equals pi r squared ds for the small ds dt for the small pool. So then now I go on to solve the equation. And to solve the equation, I start by putting both of the equations equal to each other. So it's pi r squared db dt, this for the big pool, and then equal to pi r squared ds dt, this for the small pool. So then once I do that, then I can plug in what I know. So since they give us the radius for the small pool, I know this, I know the radius for the big pool, and then they also give us the radius for the small pool, which is here. I don't know dv dt, so this is what I'm trying to figure out. And they also give us the changing rate for the small pool, which is this. So then I go on and then I plug it in. I plug it into both of the equations. So I get pi times 8, because this is the radius for the big pool, square, and then I don't know the dv dt, this is what I'm trying to solve for, equals pi times 5 squared, this is the radius for the small pool, times the rate and change of the rising water in the small pool, which is 0.5 meters per minute, which I didn't label. I will then. And then so then I get, once I multiply that out, I get pi times 64 dv dt equals pi times 25 times 0.5. Then I divided this side, the 64 pi, by this side, and then I get dv dt equals 25 pi times 0.5 over 64 pi. Then I keep on solving it to where I get dv dt equals 12.5 pi over 64 pi, and this is my answer. But then if I want to approximate it, this is what I get. Once I divide both of this, I divide this by this, I get 0.195 meters per minute, and this is my answer. So at 0.195 meters per minute is the changing rate of the big pool. So the changing rate in here is 0.195 meters per minute, and then the change in the small pool, it was given to us, and we know that it's 0.5 meters per minute, and that's my answer.